My name is David McGee, and I'm going to be starting a position as an assistant professor in January 2012 with a focus on paleoclimate. I come to MIT from a postdoc at the University of Minnesota and graduate work at Columbia University and Tulane University. My research focuses on reconstructing the history of the Earth's climate, and one of the things that I focus on is how patterns of precipitation and winds have changed on the Earth during past climates. I'm particularly interested in how dry regions of the Earth have been different in the past. So, for example, two places that I'm focusing on right now are North Africa and the American West. These are places that are dry today, of course, but used to be much wetter. North Africa supported large lakes and human habitation and diverse biological communities. Now, of course, there's the Sahara Desert. And the American West used to have giant lakes. Lake-Bonneville was the size of modern-day Lake Michigan, and now, of course, is much drier. I'm trying to understand how the Earth's atmosphere has been different in the past. Mostly, my research is focused on the Earth's drylands, understanding how patterns of precipitation in these drylands have varied under past climate conditions, and so looking at the mean state of this dryland hydrology in different climates, but also the rates of change during periods of climate change. And so, for example, in North Africa, we know that the summer monsoon was a lot stronger, say 6,000 years ago, and has gotten weaker since. It looks like some of that change was quite quick. And so one of the overriding questions there is essentially how quickly and why can a monsoon fail, or can a monsoon substantially weaken at least? One of the neat things that I've been working on recently are a series of deposits that were left by Lake Bonneville, one of these giant lakes that was in the western United States during the last glacial period. These lakes leave clear shorelines around the basin that can be dated, but they provide just a fragmentary record of what the lake was like and when it was high and when it fell. We found some deposits that provide a nearly continuous record of the lake's history and are very precisely dated by uranium-thorium methods. And so it's allowed us to move from a story where we have bits and pieces of what the basin was like at different times and rather fuzzy age constraints to a much more continuous and well-dated sense of just when the lake rose and just how quickly it started to fall, just how quickly the region started to dry out when the northern hemisphere started warming at the end of the last ice age. So being able to really pin down what the lake's history is and relate it to other things going on in the northern hemisphere, and build links between other well-dated records that are quite far away from the Great Basin, has been really exciting. That we're starting to be able, with these well-dated records, we're starting to be able to build a more global sense of what the imprint of these past climate changes has been, rather than simply viewing these records in isolation. If they're dated well enough, they can be correlated and used to identify spatial patterns of past climate change. I also really enjoy thinking about dust for whatever reason. So North Africa is a place where it's hard to figure out what the climate used to be like because so much of it has been blown away. And so one of the ways that we look at the climate history of Africa is by looking downwind in marine sediments. Times that right now there's a lot of dust being blown into those sediments. It's the dominant contributor to marine sediments off the coast of Africa. And we can go back to times in the past when there was very, very little dust hitting those areas. And so we can use those changes in the amount of dust as an indicator of what the climate was like back on the continent. And then we can work with modelers who incorporate dust into their models to try to figure out what kind of climate conditions would have probably corresponded to those amounts of dust. So that's using dust as a passive tracer. Dust also actively impacts the climate. So it supports important parts of the ecosystem of the surface ocean in the North Tropical Atlantic and other areas of the world's oceans. It also has important radiative impacts, so it can actually sort of feedback on and reinforce patterns of sea surface temperatures and atmospheric circulation that made it dusty in the first place. And so trying to understand dust's role in past climates, trying to use dust to probe past climates is something that is an area where there's been good work done in the past, but I think there's a lot more that remains to be done. It's one of the few things that can help us to reconstruct past wind patterns and past patterns of surface wind speeds and directions. And so it may not sound exciting to say that you're really interested in dust, but it's one of the things that I really enjoy thinking about.